let's resume the session. And if we have time towards the end of the day, I have a video that talks about wind turbines, just to complete the conversation from yesterday. But let's continue now talking about solar power. And whenever somebody talks about solar power and energy, the first thing that comes to mind is photovoltaics. And we just spoke about photovoltaics, but there is much more about solar than photovoltaics. And the next technology, what we call concentrating solar, the reason why it has attracted a lot of attention is that it relies on infrastructure that we already have to produce electricity. That means turbines, thermodynamic cycles. So I'm going to show you a couple of videos, and then we'll talk about the technology in a little bit more detail. So.
Okay, take the natural heat from the sun, reflect it against a mirror, focus all of that heat on one area, send it through a power system, and you've got a renewable way of making electricity. It's called concentrated solar power, or CSP. Now, there are many types of CSP technologies: towers, dishes, linear mirrors, and troughs. Okay, have a look at this parabolic trough system. Parabolic troughs are large mirrors shaped like a giant U. These troughs are connected together in long lines and will track the sun throughout the day. When the sun's heat is reflected off the mirror, the curved shape sends most of that reflected heat onto a receiver. The receiver tube is filled with a fluid. It could be oil, molten salt, something that holds the heat well. Basically, this super hot liquid heats water in this thing called a heat exchanger, and the water turns to steam. Now the steam is sent off to a turbine, and from there, it's business as usual inside a power plant. A steam turbine spins a generator, and the generator makes electricity. Once the fluid transfers its heat, it's recycled and used over and over. And the steam is also cooled, condensed, and recycled again and again. One big advantage of these trough systems is that the heated fluid can be stored and used later to keep making electricity when the sun isn't shining. Sunny skies and hot temperatures make the southwest U.S. an ideal place for these kinds of power plants. Many concentrated solar power plants can be built within the next several years. And a single plant can generate 250 megawatts or more, which is enough to power about 90,000 homes. That's a lot of electricity to meet America's power needs.
Okay, so the idea here is very simple. You still have a turbine. That turbine spins. It's connected to a generator. You can produce electricity. One of the challenges is the type of working fluid that you use for your turbine. In most cases, we would like to use water. In some cases, you have to use a heat exchanger because part of the thermodynamic cycle may use like a molten salt. And the reason why molten salts have become so attractive is that because they can store a lot of energy. And probably one of the most important properties is because of the heat capacity. The heat capacity is a property of all materials, and it gives you a measure of how much energy you need to supply a material to increase its temperature. But conversely, it can also tell you how much energy can be released by cooling or heating that material. Okay? So materials that have good heat capacity include water, and that's the reason why water is used for cooling applications, because the heat capacity of water is pretty good. Helium has high heat capacity, and that's why helium is considered for gas-cooled reactors as the working fluid. But there are some materials, like salts, that have also high heat capacity. And there is another property. It's called the latent heat of fusion. Every time you melt a material, you have to add energy, okay? So if you have a plot, if you plot let's say that we're going to plot here temperature, and here we're going to plot heat. If you have a, let's say, a liquid, you can apply heat, and it's going to change temperature. Let's assume that this is solid. So if we are here on the solid phase, we apply heat, the temperature is going to increase, okay? And the slope of this is going to be what? What's the slope of that curve? Okay? So the heat capacity is going to be proportional to this slope. Now, when the material melts, goes from the solid to the liquid, what's going to happen? Okay? Every phase transformation happens under isothermal conditions, constant temperature. And once you go from the solid, and then you go to the liquid phase here, what's going to be this slope? It's the heat capacity, okay? But now this is the heat capacity of what? Of the liquid is the heat capacity of the solid, okay? And what's this value of heat right here? Very good. So this is the latent heat of fusion, okay? Or heat of melting. What happens if we continue and reach the boiling point? What happens then? Okay, so it's going to be a phase change. Okay, this is the melting temperature. This is going to be what? The boiling temperature. And this is going to be the what? Evaporation. Okay, and then after this, it will go here. And what's going to be this slope? Heat capacity of the gas, okay? So this is the principle behind selecting working fluids for thermodynamic systems. And if you remember in the video, they talk about molten salts. Molten salts are very attractive because there are some molten salts that have a very large heat of fusion. So as long as the molten salt is in a liquid state, everything is working well. When the sun disappears, you can use a lot of the energy stored in the molten salt to still produce electricity, okay? That's what we call a phase change material concept. You can use phase changing materials as a way to store energy. In the case of the molten salt that people use have very large latent heat of fusion, and that heat can be used at night when the sun is not shining to still produce steam and to move the turbine. Another application of this concept is in insulation. You can actually build walls for buildings with these phase change materials. And you can have little capsules embedded on the walls, so if it's very hot, those capsules will absorb the heat and melt, and will provide a comfortable temperature inside the room. And then at night, when it gets cold outside, this phase change material will solidify, and they will release heat, and that heat can be used inside the building for temperature comfort. So this is one of the biggest areas of research, and is the area of phase change materials. Okay, so this is an example of how we have used molten salts to store energy, but in the area of building applications, this is a growing area. People looking for phase change materials that can be incorporated into the walls, into the roof, to reduce the energy needed to provide air conditioning inside buildings. Okay, so let's take a look at another video of concentrated solar.
In the 1980s and 90s, U.S. Department of Energy projects in California demonstrated that power towers could collect and store heat to generate utility-scale electricity 24 hours a day. And today, power towers continue to build a clean energy economy. In 2009, a modular two-tower system with 24,000 mirrors in the Mojave Desert powers more than 5,000 homes. And in 2010, construction began on a 370-megawatt three-tower system with nearly 175,000 mirrors. This California plant created more than 1,000 jobs and powers more than 350,000 homes. Let's shine some light on the point-focused technology behind power towers. Thousands of mirrors called heliostats reflect sunlight onto a receiver on top of a tower. These computer-controlled mirrors move to maintain this focus from dawn to dusk. In a steam power tower, water is pumped to the receiver where concentrated thermal energy heats it to over 1,000 degrees Fahrenheit. Some of the superhot steam is stored in a tank, while most is sent to the power block. Here, high-pressure steam spins a conventional turbine to produce electricity. One of CSP's great advantages is that thermal energy can be stored for later use. If a cloud blocks the sun, the steam stored in the tank is used to continue to produce electricity for up to an hour. Another system uses molten salt instead of water. Cold molten salt is pumped to the receiver, where it is heated, then flows to a hot storage tank. The hot salt then flows through a heat exchanger, where heat is transferred to water, producing steam that spins the turbine. The molten salt then flows back to the cold storage tank. In extended cloudy periods or at night, the stored hot salt can continue to produce steam and generate electricity reliably for hours. Today, innovation continues to drive down costs and boost efficiency, so power towers can supply utility-scale power, providing dependable, clean electricity to homes, businesses, and communities. Power towers reflect America's shift to a prosperous, clean energy future.
So, questions about concentrating solar? Is that clear?
I was thinking about the melting temperature of the salt.
Salt, yeah.
Because they are always like molten, or
That, you know,
they could convert to solid and then you use the more.
that is a very good question. So the question from your colleague is it always molten or if it solidifies? And that's a problem because if it solidifies, and it will plug all the pipes, and then you got a big problem. So when they do the engineering of these systems, they have to provide always some level of heat. So you have some level of temperature where the salt is in a liquid state. That's a good question. Now, if they see that temperatures are going to drop outside in the environment very low, you will need to provide some energy to the system to prevent the salt from solidifying. If the salt solidifies, you can have a very serious problem. If you think about water, what happens when water goes from liquid to solid? It expands, okay? Now, that's a very anomalous behavior. Not all materials do that. In fact, other materials, they actually shrink when they solidify. But there are some molten salts that behave like water. And the last thing that you want to have is your pipes exploding because of solidify. So that's a good question. That's always a challenge. How do you engineer your system in a way that you always maintain a certain low temperature that will be above the melting point of the salt? Now, there's something called heat tapes. If you have done experiments in the lab, there are some heating tapes that you can wrap the pipes around, and all you have to do is pass a current through the tape, gets hot because of Joule heating, and keep some minimum temperature. That's usually what they do in these systems. They use some insulation, some heat tapes, and they always keep some minimum temperature to prevent the solidification. So that's a good question. You know, what type of molten salt do you use? Well, you gotta be looking at the melting temperature. The melting temperature cannot be very high because the heat that you collect may not be high enough to take it into the liquid state. And there's a lot of work trying to come up with molten salts. And guess what? Quantum mechanics actually comes to the rescue because you can predict all these properties from quantum mechanics. In fact, it's a combination of density functional theory and molecular dynamics simulations that you can do to find out all these properties. And that's how we do a lot of this selection of materials for this application. So that's a good question. What else? So let's assume that that you get hired by this company that is a utility company, and they tell you, okay, you need to make a decision whether to use photovoltaics or concentrating solar. How do you decide what to use? Let's assume that your clients are, you know, a community of 10,000 homes, and you need to provide electricity for them. And it's going to be your decision to tell the company what type of investment. Should you buy solar panels, or should you install concentrating solar? What type of thought process will you go through to decide which is better than the other? You think concentrated is better? Very good, okay. So that's very good. That's one of the main considerations. Can you provide energy 24 hours a day? With photovoltaics, you cannot unless you put some batteries, okay? And we talk about batteries on Monday. So if you buy batteries to store energy and provide energy when the sun is not shining, then the answer is yes, but that's going to add to the cost of the system. So this is the problem with all this intermittent source of energy. The same is true about wind. If the wind is not blowing, you know, you got to store energy somewhere. And this is why when I show you those slides and when we talk about wind energy, you have a bank of batteries that will store energy to provide whenever the wind is not blowing. The same thing is true for this. So that's probably the main consideration. You know, when you do your calculation is, do I have the storage capacity? Do I have the storage capacity to provide energy at night when the sun is not shining? So that's number one. Okay, that's very good. Number one. What else should you consider when you look at the cost of this? Very good. That's an excellent point. If you remember, when we talk about this source of energy, we call them diffuse types of energy. You need a lot of area when you use photovoltaics. I mean, the amount of area that you need for photovoltaics is very large. So what you do is you do your calculation. Say, okay, let's assume that I want to provide 200 megawatts. With these concentrating solars, I mean, you still need some area for the mirrors, but the amount of surface area that you need is much less than what you will need with photovoltaics. So that's very good. Energy storage, surface area. So if you're a utility, you know, if you're going to be providing electricity, you have to buy the land. And sometimes the land is not cheap. You have to pay for the land. So if you need a lot of area for photovoltaics, that's going to add to the cost of the system. What else? Energy storage, surface area. What else? Yeah. Absolutely. So weather conditions are very important. Now, we have all these maps, and in fact, I guess at this point, every country now has pretty good idea what the type of weather conditions. So there are some geographical regions where it will make some sense. Now, clouds will affect both equally because you still need, you're always concerned with clouds. So geographical conditions has to be one of the most important considerations. So there are lots of things, and a lot of these decisions, some are technical, like the energy storage, some are economical, like the surface area, like the geographical location. So these are not simple decisions, and this is why there are so many options that people are still investigating. People are investigating because I don't think it's very clear that you can have an answer for every condition. The answer is going to be, it depends, okay? And by the way, Spain was one of the leading countries when it came to concentrating solar. The US actually purchased some plants in Nevada that were designed and built by the Spaniards. So concentrated solar, Spain had a technical leadership in that area. Now, from the materials perspective, if you're a materials scientist or a materials engineer, things that you need to be concerned with concentrated solar include corrosion resistance. Sometimes these molten salts can be aggressive, and therefore the type of piping that you use needs to be the right pipe material. Otherwise, you're going to have corrosion problems. These things can get really hot. So you are not going to put plastic piping in this system. You need to put metallic piping. And sometimes iron-based alloys are not good enough. You have to go to the nickel-based super alloys because they can take better, they can behave better at higher temperatures. And once you go from iron-based to nickel-based, the expense goes up. Another problem that if you remember the first video, one of the configurations used these parabolic mirrors. So you have and then in the center you have a tube. With the fluid. So the sunlight goes here, and it reflects into the tube. And then you can have direct incident light. So if you look at a pipe that is subjected to heat fluxes that are not uniform, what happens to the pipe? Deformation. So every time you have temperature gradients, you're going to have stresses. So if you look at the stress condition for this pipe is going to be subjected to some pretty complex states of stress. And every time the lighting conditions change, the pipe is going to be doing this, okay? And that's what we call thermal fatigue. This is a very serious problem for structural materials, especially for pipes. And we have seen cases, we work with a company called Babcock and Wilcox, that they have cracked pipes in concentrated solar systems just because of the thermal fatigue. It gets so hot and the irradiation is so non-uniform that you can actually crack nickel-based superalloy pipes. And there is really no easy solution. There is really no easy solution, and this is why the mirror approach is actually a little bit better than this approach, because the structural reliability of the pipes in this condition is an issue. You can crack the pipes, and that's something that nobody will think about it. Metallic pipes, hey, no problem. The stresses are so high because of the irregular flux conditions, and the fact that the sun is going in and out. Every time the sun goes in and out, you have a cycle. And you do this long enough, you're going to have problems. So that's another decision whether to go from this configuration to the towers. In the case of the towers, it's a little bit better. Something to be concerned about the towers are the mirrors. What if the mirrors get dirty? You got to have somebody going there once a week to clean up the mirrors. Some of these mirrors are mechanized. They have to track the sun, so things can wear out. These are complex systems, but this is a major player. And the fact that you can get power over relatively small surface areas makes concentrating solar fairly attractive. More questions? Uh-huh.
I was wondering which is the country, the northest or southwest country, which would have molten salt plants. Because I was thinking
bad idea there, yeah. Yeah, so if you remember, we had a map. Let me show you that map. So this map is really going to tell you where these things make sense, okay? So this is the Tropic of Cancer, right about here. This is the Tropic of Capricornius over here. Somewhere in between, I mean, that'll probably be the best answer. Somewhere in between the tropics, that's where you will probably have the best results. North of that, it gets really challenging, unless you go to places like the Southwest. I mean, look at the anomaly here in the Southwest. This is way north of the Tropic of Cancer, but here the conditions in Arizona, Nevada, California, they are really good. I mean, this is probably some of the best conditions to use some of that. But once you get to Canada, that's really unknown. I mean, it gets way too cold in the winter. The solar irradiation during the year is really not that good. Even the northeast of the U.S., I mean, you will probably never see anything like that in the U.S. The only part in the area where this will make sense is on the Southwest. You can go to Hawaii. Those are more or less good conditions. But, you know, these are perfect locations. You know, I mean, most of the northern part of Africa, Australia, those are areas, regions where, on average, you get good conditions. And then the fluctuations throughout the year are pretty mild. So, yeah, the last thing you want to do is instead of producing power, spending power, just keeping your plant in operational conditions. So yeah, you know, I've been working with people in Ecuador, and Ecuador has done a very good. You know, I give Ecuador a lot of credit. They've had very proactive administration in the last few years. The president is named Rafael Correa. I don't know if you know Rafael Correa. And I give Ecuador a lot of credit because most countries in Latin America have been pretty corrupt. And even though there are lots of resources, you look at the conditions are pretty poor. But Ecuador, you know, we got to give them credit because they have made a significant investment in alternative and renewable sources of energy. Ecuador has a lot of oil, and their economy is really depending on oil. They didn't have any gas. And just to give you an idea of the size of the efforts that they have made, every kitchen in Ecuador uses natural gas, okay? But Ecuador doesn't have natural gas, so Ecuador imports gas to supply, and they actually subsidize the gas. So every kitchen in Ecuador, you know, you buy these little tanks of gas. They are painted blue, and that's how you cook. And Correa said, you know, this really doesn't make any sense. We really have to change that. So he started a national program, and he said, we are going to electrify every kitchen in Ecuador, okay? So we are no longer going to use natural gas for cooking. And they came up with a concept, it's called induction stoves, okay? And he said, we have so much water that we're gonna build 3 big hydroelectric plants to produce a lot of electricity. And the electricity is gonna be so cheap that we're gonna be able to electrify every kitchen in Ecuador. So if you go to Ecuador right now, there is a program where the government is actually subsidizing the purchase of these induction stoves. And the way they work is that you pass an electric current through a coil. You have to use a pot that has to be an iron-based pot. And then by induction, you can heat it up. And they are very efficient. So now everybody is getting their little induction stove. It's all electrified, and they no longer have to use natural gas for their kitchen. So, you know, this is one of these big national programs that makes a lot of sense. And so they are exploring a hydroelectric power. They are building a bunch of dams, but they have also installed a lot of wind turbines. And before they made those decisions, they actually spent like 5 years doing very detailed studies of how the wind blows in Ecuador. The Galapagos Islands, on the Sierra, on the ocean side, whether it's Guayaquil or Quito in the north. I mean, they have these very detailed maps, and they know exactly how the wind blows at 2 in the morning, 10 a.m. In the morning, 2 o'clock in the afternoon. They have this type of information for the sun. So all of the decisions that they have made at the national level are based on very good information. And this is exactly what's going to happen. So your colleague says, does it make sense to install concentrating solar? Probably yes, but probably not. It just depends on what the conditions are. And if you go to the Galapagos Islands, now they have these wind turbines, and they are actually supplying a lot of the electricity in some of the big islands in the Galapagos. So a lot of credit to Ecuador. But this is the type of questions that they are answering. Does it really make sense? Should we install photovoltaics? One thing that we're going to talk about here in a minute is hydrogen. And Ecuador wants to have a national program using hydrogen. And they want to use hydrogen not just as a fuel, but as a way to store energy. Okay? And we're going to talk about here. So does that answer your question? Okay. More questions? No? Okay.